In addition to static waveforms, we also have dynamic waveforms, implying that the signal changes in time. And also, we can have dynamic and aperiodic or dynamic and periodic waveforms. So aperiodic is going to imply no repetitions in y of t if it's an analog signal, or y of n if it's a discrete or digital signal. Now, one signal that's dynamic and aperiodic that you'll see a lot of is a step signal. So a step signal has an abrupt change at some time t0, and it changes from an amplitude of 0 to an amplitude of a0 at that time t0. And to write this mathematically, I'll say that y of t, I use the term u for a step function, t minus t0, implying that the step happens at t0, and I can give this an amplitude a0 associated with this. And this u of t is kind of our base step function. This implies that I'm 0 at time less than 0, and I'm 1 at time greater than 0. And so by adding this t minus t0, that basically means that I'm stepping up at time t0. So another dynamic and aperiodic waveform that I might see commonly is a pulse waveform. And I'm going to draw all of these in analog, although obviously you can discretize or make them digital as well. Now this pulse waveform will go to some amplitude a0 at time t0, and it will fall back to 0 at time t1. And I can write this as a difference between two step functions. So my y of t for a pulse is going to be a0 times u of t minus t0 minus u of t minus t1, whereas u is defined as that step function that I gave you earlier. And there are obviously a lot of other dynamic and aperiodic waveforms as well. The impulse and the ramp are probably two of the most common of those other dynamic and aperiodic waveforms. So we also have dynamic and periodic waveforms. And periodic, which basically means that the waveform repeats itself in time. So at all times t, y of t is equal to y of t plus some period, which is defined by this big capital T. So a great example of a dynamic periodic waveform is a simple sinusoid. A simple sinusoid just has one frequency component. And given a frequency of that sinusoid omega, the period of that sinusoid I'm going to define as this capital T is 2 pi over omega. So I have a phase of my sinusoid phi, and the time in this case that I cross this 0 point will be t phi is minus phi over omega. In this case, I also have some DC offset to my sinusoid a0, and we'll talk a little bit more about DC offset in a bit, but it's basically shifted up from 0. And I have an amplitude for my sinusoid c. So this signal goes from a0 minus c to a0 plus c at a peak of the sinusoid. So I can write this entire signal as y of t is a0 plus c times sine omega t plus phi. And this is a dynamic and periodic waveform. It's both changing over time and it's repeating itself in time. So complex periodic waveforms are going to contain more than one frequency. And this is an example of a complex periodic waveform over here. If I repeated this in time, or I provided more time data of this waveform, you'd very clearly see it repeating itself in time, and you'll see that a little bit later. But these signals these are ubiquitous, right? These complex periodic waveforms are all over the place. So I could be measuring some kind of signal that happens to be periodic. I could have some 60 hertz noise on top of that signal from just the wall power outlets. I could have some other kind of higher frequency noise components on my signal as well. But my signal is basically composed of all of these sinusoids of varying frequencies. So let's look at how I actually created this yellow waveform here. So I started with a single simple sinusoid. So this would be a dynamic and periodic waveform. So y1 of t is just 5 times sine of t. So my frequency is 1 rad per second, my amplitude is 5, I have no DC offset to this. So it just looks like this red line here. And then I can take that and I can add to it another sinusoid. In this case, my frequency is 2.5 radians per second. I have an amplitude of 3, that same 0 DC offset there, no phase shift on this either. And when I add those two waveforms together, I get that yellow signal that you saw earlier. And so the signals that you get from the real world are going to look a lot like this. They're going to look like all of these sinusoids superimposed on top of each other, and we'll talk a lot about a way to better analyze those waveforms and a better way to talk about them in terms of their frequency component.